Hello everyone, today's topic is a review about force. Here we want to find the components and the resultant of force. Okay, let's see how we can represent the force that work on a body. So here we have the bracket which hold the cable which is in tension. So how to draw the force on the body, on the bracket? Okay. Here we can see that the force of P, which represent the cable tension. So it's work on the direction with the cable. So it has the similar angle, the same angle theta. And let's see, the point of application of this force will be the hinge, the pin that is point A. Okay, so the location of this point of action is very important because it has effect on the rigid body. Okay, so then next is the principle of transmissibility, which is the properties of force. Here we have the rigid body, and we have one single force of P, which is directed on the right hand side, right forward, and it is work at point A. Okay. So now this force has the line of action. Okay. This force has the line of action, which is represented by the dashed line. So it is the extent of the vector of force. Then, so what does this mean? The principle of transmissibility allows us to reposition or move the force of P. So initially, it is work at point A. The point of application is initially at A. But then, using the principle of transmissibility, we can move this force along the line of action. So for example, here we move at point B. So B is the new point of application of the force P. Does this affect the rigid body? No, because we assume that the body is rigid. So that means it will not deform during the loading, during the application of force. So it is same effect if we apply the force at point A or at point B. But for the flexible body, when we consider the deformation, the effect may different. So if we apply the force at point A, then the deformation will be like this. But if we apply the force at point P, then the deformation should be like this. So it has the effect if we consider the body as a flexible. But when we assume the body is rigid, the deformation can be neglected, then we can freely move the force along the line of action. So for example, in the previous example, we have the cable tension, which is work at hinge at point A. So we can extend the line of action, which is directed along the force P. So using the principle of transmissibility, we can move or reposition the force of P in the new location. So then how we apply this concept to find the resultant of forces. So for example, here, we have two external forces, F1 and F2, work at the same rigid body. Both of them are work or applied at the common point, that is point A, so that we can call them F1 and F2 as the concurrent forces because they share the point of application. Then to find the resultant, just apply the parallelogram rules. Okay, so you draw the parallelogram set here, then take the resultant from the point of application to the intersection of the vector of force F1 and F2, as shown in this figure. Okay. And we have to remember that the resultant of force should be applied from the same point of application of F1 and F2. Then how if we have F1 and F2 work at the different point of application? Okay. So for example, here we have F1. This is the point of application of F1. And here we have point of application of F2. Then how we can get the resultant of these two forces? So using the principle of transmissibility, we can extend the line of each vector F1 and F2 so that they make an intersection. And this intersection we give the point of A, which represent the point of application, the common point of application of both vector F1 and F2. So then we have to draw the resultant of force from this point. Okay, so just reposition F1 into point A and F2 also into point A. Then find the resultant, the magnitude and the direction using parallelogram rules. Or we can also find the resultant from the triangle rule. But we have to be careful. We have to apply the principle of transmissibility. So for example, here we have F1 and F2. We remove or reposition F1 into point A. So we have the new location of F1 at point A. Then we can redraw the F2, but here we don't use the parallelogram rules, so we cannot drawing the F2 here. But instead of using parallelogram rules, we move the F2 into the head of F1 so that the tail of F2 is coincide with the head of F1. Okay. Then by doing so, we can obtain the resultant of forces F1 and F2. And then we have to notice again that the resultant of forces that we have here is also plot or drawn from the point A, the common point of application here of F1 and F2. Okay, so we have to remember that. So this is the correct method to obtain the resultant, both triangle rules and parallelogram rules. So mathematically, we can write the summation of vector F1 and F2 as shown in this formula. And here, I said that we have to be careful when doing the force transmissibility. So, and apply the triangle rules because it can misleading we can obtain the wrong resultant of forces. So for example, here we can drag or move this F1 at point A so that it has the point of application at A. This is true, this is correct. But then if we reposition F2 also so that it applied at point A, but the location of the tail of F2 is outside of the point A, then it will give us the resultant of force, which is not started from point A. So here, the resultant of force is not passed through the point of application, the common point of application. This is wrong because it can change the movement of the body. It can create the moment here. So this is the wrong way, the incorrect method to obtain the resultant. So the resultant must be in this location. It must go through, it must pass through the point A. I hope that you can understand this. So in the previous discussion, we learned how to sum or obtain the resultant of two forces, which is concurrent, and they make the intersection at the common point of application. Then how if we have special condition here that F1 and F2 is F1 and F2 are parallel forces. So if we draw the line of action of F1 and F2, it is impossible for them to meet at the intersection point because it is parallel. So how to draw the resultant of this force? Because we have to draw it at the common point of application. So here we modify the force by adding the virtual force. So actually this force F and minus F is not appears, that they don't exist in the body. It's just a mathematical modification. Okay. So what is the benefit of adding this imaginary force is that we can obtain the R1 and R2 from F1 and F2 consecutively. Okay. Then we can see that the direction of R1 and R2 can make an intersection. Okay. So the line of action of R1 and R2 intersect at this point. So we call this point A. So this is the common point of application of R1 and R2, because R1 and R2 consists of F1 and F2. So this common point of application also applied for F1 and F2. Okay. So now we have R1 and R2 start from this point of application. That means we can draw the resultant of R1 and R2 from this common point of application, from point A. Okay. Then now we can obtain the direction and the magnitude of R. Okay, so we have the common point of application here. We know the direction and magnitude of R. So where is F and minus F go? Because we add R1, which consists of F1 plus F, and R2, which consists of F2 plus minus F. So this will cancel each other. That means this resultant only consists F1 and F2. Okay, so this is the special condition. We need to modify the force with by using this imaginary force to obtain the resultant, to obtain the point of application, so that we can draw the resultant of force. So now, how we can obtain the components of forces? So to obtain the component of forces, we can decompose this vector into the horizontal axis and the vertical axis, x and y. So here we represent the vector of F, which has the direction theta measured from the horizontal line, and it has the magnitude here, which represented by the length of F. So we can, using trigonometry, we can define or describe Fx and Fy. So if we see F as a vector, it has component in the x direction and y direction. Okay? And by trigonometry, we can obtain this formula. So knowing the component in x and y direction, horizontal and vertical direction, it allows us to obtain the resultant of Fx and Fy. So we can use the Pythagoras rule to obtain the resultant back. And to check the direction, the theta is represented by the gradient of this force. So here is the example of force decomposition with in different situations, in the different problems. Okay, so here we split up, we decompose F in x and y direction. So we need to measure the angle from one of the axes, can be x or can be y. Okay. So next, the difference between the first and the second figure is that here we the zero point, the reference point of x and y is not coincide with the point of application, but it will not change the fact that we can still decompose F into x and y direction. Okay, but we must be consistent with the rules of decomposition. Okay. So here we have the positive x-axis of x is direction upward. This is the plus, and so that here is the minus. So it is a fact that decomposition force. So in Fx, it is directed downward, so it is negative. And y also negative because it goes downward here. So we must be consistent with this direction. Okay. So then you can explain the two others condition here to obtain the components. So now we have the example of force components. So we have one bracket and we have three external force work on this bracket at the same location with the same point of application here. So we can call this that F1, F2, and F3 are the concurrent force, okay, because they share the point of application. Then how to obtain the components of each force here, and where we have where we have to draw the components. Okay, so first is F1. Let's see here that we draw the components F1x and F1y from the point of application of F1, that is point A. This also applied on F2 and F3. We must draw each component from their point of application of the original force. Okay, so now we have at point A 6 forces: 1, 2, 3, 4, 5, and 6. Okay, so we can decompose these 3 forces into 6 components in X and Y direction. And we must remember that all the components must be drawn from the same point of application of the original force. Now we have another example in obtaining the resultant of forces. We have 2 external forces applied on the structure at point P. So point P is the point of application. Both forces work in this point. So this is the common point of application, and P and T are the concurrent forces. Okay. So now let's see how to obtain the resultant. Using transmissibility principle, we can move or reposition the force P so that the tail is at the point of application. Okay, because T already in the right position, we don't move or reposition the force of T. Because we have both P and T already applied in the same point of application here, then now we can draw the resultant of forces using parallelogram rules. Another way to obtain the resultant is by moving or reposition the force P. We move so that the tail coincides with the point of application here. Then instead of using parallelogram rules, we use the triangle rules. So we move the force of T not using the principle of transmissibility, but using the factor analysis. So we add the factor by put another factor by put the factor into the head of the other factor. Okay, so the tail of T meet with the head of P. So by doing this, we can apply the triangle rules. And here again, we can see that the resultant of forces is drawn from the point of application to the head of the last factor, that is T. Okay. So both of them are correct. Okay, so we already discussed about the forces as a factor so that we can decompose or obtain the resultant. And we also notice, and we must remember that when we doing the summation or extraction of forces, the point of application is very important. Okay, so make sure that decomposing or adding the factor to obtain the resultant must be drawn from the point of application. Okay, so let's have the exercise.